Everybody, today is Friday, October 27th, and we are going to summarize and finish Chapter 5. And what we've done in Chapter 5 is shear moment diagrams. And we have done them graphically, and we have discussed how to do them using the equations for load, shear, and moment. And today we are going to finish our discussion of design. All right. Now, when we talk about design, first of all, what we are talking about is the idea that every place on the structural member must be able to bear every load with room to spare. So in other words, we over-design to an appropriate degree. To minimize the chance of failure. Okay? So that's what this section is about, because, as I've said over and over again, failure is an option, but it's a really terrible option. And we just do not want it to happen to us. So let's take a look at a problem and just bring these ideas together. We've already talked about all of these ideas. For example, we talked about the shear moment diagrams graphically. And then we talked about shear moment diagrams constructed with equations. And basically, the equations just amount to this. dV dx is equal to negative W for a distributed load. And a dm dx is equal to V. And those are both separable. They can be written as separable differential equations. Now, on both of these, whether you do it graphically or with the equations, the initial conditions are found using statics. In other words, summation forces X, possibly summation forces Y, and summation of moments. But when we separate this, as I pointed out, the integral of dm becomes m sub f minus m sub 0. And similarly here, v becomes v sub f, the integral of dv becomes v sub f minus v sub 0. So we're really talking about the initial and final conditions and the space in between them. And we can interpret that as the area. All right? So when we design, we want to design so that nothing ever fails. So let's take a look at a problem that is after section 5.3, which is going to talk a little bit about all of these ideas pulled together. So in our textbook, I'll start with, let's look at problem 566. Ugh, I gotta put this underneath. Okay. Okay, am I all right? Yep. So problem 566. We have a beam. Let's do 565 and 566. So let's start with 565. It says, for the beam and loading shown, design the cross-section of the beam knowing that the grade of timber used has an allowable normal stress of 12 MPa. So sigma allowable is 12 MPa, and we need to design for 12 MPa. or less. So we start out the same way that we've always started out. We draw a diagram which shows what the prismatic member looks like. And in this case, we have a fixed support at A, a rolling support at D, and at B and C, we have point loads, which are 1.8 kilonewton and 3.6 kilonewton. And in between, we have 0.8 meters, 0.8 meters, and 0.8 meters. So the entire length of this beam is 0.8 times 3, which is 24. The loads are placed in a symmetrical manner, but the values are not symmetrical, so we have to go through, we need two equations and two unknowns to find our reactions at A and B. And we're told that the cross-section looks like this. It's 40 millimeters wide, so since I'm going to keep everything in meters, I'm going to call that 0.04 meters. And what we're designing for is some height. So in other words, how tall does this have to be in order to not exceed an allowable load of 12 MPa? All right, so once again, start with our good statics. We have a reaction at A, reaction at D, point loads of 1.8 and 3.6. So the first thing we know, summation forces Y equals 0, reaction at A plus reaction at D minus 1.8 minus 3.6 equals 0. Reaction at A plus reaction at D equals, these come over as positives, 5.4 kilonewtons. Since the loads are not, the values of the loads are not symmetrical, we have to write this, we have to do a moment equation in order to find our reactions. So let's do summation of moments about A, also have to be equal to 0. So we put a pin here. The 1.8 kilonewton load, which acts 0.8 meters from A, creates a clockwise rotation, so that's negative. 3.6 kilonewton load, which is 1.6 meters from point A, also creates a counterclockwise rotation, or excuse me, clockwise rotation, which is negative. And my R sub D, which acts at a distance of 2.4 meters from A, creates a counterclockwise load, which is positive, and the three of those things sum together equals 0. So the reaction at D, if I keep this on the left-hand side, is equal to 1.8 times 0.8, which is 8 times 8 is 64. Carry that. 8 plus 6 is 14. So that's going to be 1.44 plus 3.6 times 1.6. 6 times, I'm just going to do my calculator. 3.6 times 1.6 is 5.76. Equals RD times 2.4, or I can divide that by 2.4 to get the value of RD. So I take 1.44 and add it to 5.76, divide it by 2.4, and I get a value of 3. So the reaction at D is 3. I've been consistent, loads in kilonewtons, distances in meters, so it's 3 kilonewtons. From here then, I know that R sub A plus R sub D is 5.4 kilonewtons. So if R sub D is 3 kilonewtons, this is 2.4 kilonewtons. Okay. All right, so now I'm ready. Now I've got my load diagram. I need to do a shear diagram. And then I'll do a moment diagram underneath. So every time that there's a discontinuity or an application of load, I'm going to have something different going on. And the way I like to view that is by a cutaway. So from here to here, I have 2.4 kilonewtons pushing up, V pushing down. So my equation is 2.4 kilonewtons minus V equals 0, or 2.4 kilonewtons equals V. That means from here to here, I have positive 2.4 kilonewtons on my V diagram. Now, after between the two loads, 2.4 pushing up, 1.8 pushing down, cut away V. So I have 2.4 minus 1.8 minus V equals 0. 0.6 equals V. So from here to here, I drop to a positive 0.6 kilonewtons. And then in the last half, I can just continue cutting from the left, or I could cut from the right. And I could say 3 kilonewtons pushing up. And then I draw my V like this. And so I have 3 kilonewtons plus V equals 0, or V equals negative 3 kilonewtons. So negative 3 kilonewtons equals V. Okay, now I could have constructed it the same way. I would have 2.4 minus this, 2.4 minus 5.4. So if I would cut it on the other side, I would have 2.4 minus 5.4 minus 3 minus V equals 0, V equals minus 3. So it's going to be exactly the same value whether I cut from the right or from the left. All right, so now for my moment diagram. Okay, from here to here, oops, let's see, let's get everything on here that we can. All right, from here to here, here at the fixed support, we have no moment. We don't have an overhang, we don't have a cantilever, so we know that we're going to have, I wish I had more room on this. Let me see if I can widen this a little bit. I don't think I can. Oh, I can. There we go. Okay. So from here to here, what I have is, when I draw my cutaway, I'll draw it over here, even though I'm up here. You see that? Yes. Okay, so we have a 2.4. We have some distance x, and we have a moment that is a reactive moment that we're going to solve for. So from any point between here and here, the moment that this creates is clockwise, which is negative, and its magnitude is negative 2.4 times x plus m equals 0, or m is equal to 2.4 times x. All right, so that means where x is 0, the moment is 0. And where x is 0.8, which is right before this, the application of this load, which is the 1.8. We have 2.4 times x is equal to m. 2.4 times 8. 2.4 times 0.8 equals 1.92. M equals 1.92. All right, so right here at this point, the moment increases to a value of 1.92 kilonewton meters. Okay. Now, if you recall from the lecture from Texas Tech, they talked about the fact that if these were point loads, the next order of line would be a straight line, or you can think about the area of this increasing at a constant rate. So either way, the line is going to be a straight line between those 2 points. All right, now let's go between these 2 points. Oops. Here we have a 2.4 kilonewton load, and here we have a 1.8 kilonewton load. And then we have some reactive moment. So from here to here, we have 2.4 times 0.8 plus x, because we're calling this is always constant. Then we add x, and that's clockwise, so it's negative, plus 1.8 times x plus m equals 0. So we have m is equal to 2.4 times the quantity 0.8 plus x minus 1.8 times x. Oops. There we go. Okay, well, if you take 2.4 and multiply it by 0.8, you find that this is 1.92, which is that initial condition, plus 2.4 times x minus 1.8 times x, or 1.92 plus 2.4 minus 1.8 is 0.6x. All right, so that means that the moment starts out here where x is 0, and where we come over here to where x is 0.8. Let's do this. At x equals 0, my initial condition is 1.92. Where x is 0.8, which is the maximum of that span, we get 1. This should be in, hang on a second. I just want to make sure I got my signs correct. This should be a negative, eh? But it comes over as a positive, so it's 2.4. This comes over as a negative. Okay, just wanted to make sure I had that correct. So I have 1 at 0.8, then we get 1.92 plus 0.6 times 0.8. 680 is 48, so that's 0.48. Hang on, I need to do that. So I get 1.92 plus 0.48, which is 0. 5, 4, 2.4. Yep, equals m is what it is. At x is equal to 0.8, 2.4 is equal to m. All right, so this increases, but it increases at a lesser rate, doesn't it? So in other words, my slope is increasing, but it goes here to a value of 2.4. All right, now I can go through the rest of it here, or I can see, because this is a fixed support, it's going to go back to 0, isn't it? You can also see that if I had started from this side, 0.3 times 0.8 is 2.4, which is this value. So it works from either side. All right, so the final question here is, what do I have to design this beam for? Well, the answer is sigma max is equal to minus m C over I. And I know that my cross section is rectangular, that it is 0.04 meters this way and some h, which is what we have to design for. We know, we're told in the problem, that the sigma max we have to design for is 12 MPa is equal to minus moment. Which moment are we going to use? Let's look at our diagram. In order to design, which moment on this diagram do I have to design for? Yes, the greatest, which is 2.4 kilonewton meters. Okay, so it's minus 2.4 kilonewton meters times c over I. Okay, let's think about c over I. For a rectangle, I is 1/12 base times the height to the third. C is half of the height, isn't it, for a rectangle? So we can simplify this just a little bit. Minus m times h over 2 times 1/12 times the base times the height to the third. This cancels this to squared. This cancels this to 6. So it turns out that sigma max is equal minus 6 m over bh squared. Okay. So we have this times 6 over the base, which is 0.04 meters, times the height squared. Okay, now the next question is, does it matter if this is a negative? It really doesn't, does it? Because we're going from either the top or the bottom. And since it's a rectangle, that distance is exactly the same. Okay, but we do need to make sure we get our units correct. 12 MPa is times 10 to the 6th Newton per meter squared equals, I'll just say the absolute value of this, because it doesn't matter in this case which way it is, 2.4 kilonewton times 10 to the 3rd Newton meter times 6 over 0.04 meters times the height squared. This is my design equation. So newtons cancel out, meters cancel out, and I have, let's see, let's just cancel this to 10 to the 3rd, get that rid of that one. So my simplified equation is 12 times 10 to the 3rd per meter squared equals 2.4 times 6 over 0.04 h squared. And I can solve this for h. Okay? So if I cross multiply, I get h squared times 0.04 times 12 times 10 to the 3rd equals meters squared times 2.4 times 6. Or h squared equals 2.4 times 6 over 0.04 times 12 times 10 to the 3rd meters squared. Height squared in meters squared, good units so far. All right, so let's do the numbers. 2.4 times 6 divided by 0.04 divided by 12 times 10 to the 3rd, so I get h squared equals 30 times 10 to the minus 3rd meters squared. And do I actually have a square root? I do on my little calculator. Let me do this. 30 times 10 to the minus 3rd is 0.03, right? So if I take 0.03 and I take the square root of that number, I get a height of 0.173 meters. Or if I want to report it in millimeters, it would be 173 millimeters. So therefore, for my design, I need a piece of wood that's 40 millimeters by 173 millimeters. Okay. Any questions about that? All right. So right now it is 10:34, so we have a little bit more time. I told you I'd let you go early, so what I'm going to do is I'm going to just start to work up problem 566, and then I'll leave it to you for homework, and I will give you another problem for homework as well. All right. 566 is very similar, except for now we have a distributed load. Here's A, and here is B, and we have a distributed load W of 10 kilonewtons per meter, and we're told that we have 120 millimeters wide by h tall, and we want to do the design. Once again, our sigma max is 12 MPa. All right, first thing we need to do is to determine our reactions at A and B. This is 5 meters long. This is a constant load, so that means basically we could think of this as being 10 times 5 or 50 kilonewtons, and since it's rectangular, we can think of it as being right in the middle of the beam. That means that A and B are going to have symmetrical loading, so this is going to be half and this is going to be half, or our load diagram is 25 kilonewtons, 25 kilonewtons, and of course for this we have to write that as a distributed load of 10 kilonewtons per meter. All right, so what that means for our shear diagram is right here, just a smidgen to the right of that. We start out at 25 kilonewtons. And what happens is we are going to be increasing, since this is a straight line, we're going to be increasing across, let's see, hang on, 25 minus V equals 0, 25 equals V. So we start at 25, and then we have an up, and then we come down. Over here, we're going to have a minus 25 for the same reason, and it's going to cross right in the middle, isn't it? So right there, we're going to have a shear of 0. Here, we're going to have a shear of 25. Here, we're going to have a shear of negative 25. Okay? For our moment diagram, because we have fixed supports, it's going to be 0 here and 0 here. But what's going to happen as we go across the beam? Well, first of all, we have to determine if it's going to be a negative moment or a positive moment. But because this is a straight line, this is going to be parabolic, isn't it? It's a second order. So let's just start over here. There's a couple of different ways we could do this. I'm trying to decide if I want to do it. Let's do it this way. Let's do it with the equations, just because you haven't seen this necessarily yet. So what I'm going to do is just take the equation for M in terms of V and separate that equation so that we are able to just use this. So we know that dm dx is equal to V, right? So if we look at this equation, this is a straight line, isn't it? And we know that the equation of a straight line is y is equal to mx plus b. If we consider this to be our y-intercept, we can say y, which is v, is equal to the slope times x plus 25. The slope is negative. We go from 25 to negative 25, which is a change of 50. Delta y is 50 over a delta x of 5 meters. So our v equation looks like that, right? Just because this is a straight line. So v is equal to negative 10x plus 25. So dm dx is equal to negative 10x plus 25. Dm is equal to negative 10x plus 25 dx. Integral. So the moment final minus the moment 0, I guess I would say, is equal to the integral of here from 5 to 0. So if I integrate that, I get minus 10x squared over 2 plus 25x. And since it's a definite integral, that's evaluated at 5 and 0. Okay, so you know what I really want to do? I want to get from here to here. I want to see what the value is in the middle. So let me go from, let's just do this. Let's do at 2.5 minus the moment at 0, and let's put 2.5 here, because I want to get that value right here. I already know what it is here. So the final moment, the moment at 2.5 equals the initial moment, which is 0, bringing it over to this side, minus 5x squared over 2 plus 25x evaluated at 2.5 and 0. My lower limit goes to 0. So the moment at 2.5 is 0 minus 5 times 2.5 squared over 2. Oh, wait, that's not over 2 anymore. I already did that. Plus 25 times 2.5. So the moment at 2.5 is, take 2.5 squared, and multiply that by 5. And that's my negative chunk, which is minus 31.25 plus 25 times 2.5, which is 62.5. So it looks like this is, the moment at 2.5 is a positive 31.25, isn't it? And that's going to be in kilonewton meters. All right, so since I know the shape of this is parabolic and I know my initial and final conditions, I know this is 31.25. It's positive and the shape is parabolic. So this is a little flatter than I would like to. It's not artistic liberty, it's just bad art. There we go. That's a little more parabolic looking. All right, so I'm ready for design. I know my maximum moment is 31.25 times 10 to the third, because it's kilonewton, newton meters. And once again, if I look at my cross section, this is 120 millimeters, which is 0.12 meters, and my height is the unknown quantity. So I know that sigma max is equal to, I'm going to say the absolute value of the moment, the maximum moment, times c over I. Once again, I is 1/12 base height to the third, and c is half of height because it's a rectangle. So it turns out that sigma max is equal to the moment max times 6 over the base times the height squared. And so my equation is similar to the last equation, which is the height is actually equal to the square root of, I don't want to do it that way, sorry. I didn't write it down in a form that I can pick it up really quickly. So let's just go ahead and run through this. So I know that my maximum moment, my sigma max, which is 12 times 10 to the 6 MPa, times the base, which is 0.12 meters, times the height squared, which is my unknown, is equal to the maximum moment, which is 31.25 times 10 to the third. Let's write this as Newton per meter squared. There we go. 10 to the third Newton meters times 6. Okay. So this is third. This goes away. Newtons cancel. Make sure I got all my units correct. Meters cancel. So I'm still good. All right. So height squared then is equal to 31.25 times 6 over 12 times 10 to the third times 0.12. And I can just do that, 31.25 times 6 divided by 12 divided by 0.12 and divided by 1,000. And that gives me a value of h squared is equal to 0.1302 meters. Taking the square root of that, then my height is 0.36 meters, which is 360 millimeters. Okay, so in this case, I have 120 millimeters design, 360 millimeters design, and that's what I'm looking for right there. Okay, do you guys have any questions for me? So what I would like you to do, I actually did finish that up. That's kind of surprising since I did it pretty quickly. Let's do a couple of problems that will incorporate design and some of these ideas of load. So for homework tonight, please do problem 570. That has an overhang, so the moment at B, the moment at C rather, is not going to be equal to 0. The moment at A will be 0 because it's a fixed support. Okay. And then let's do 572. And if I could find one that will require you to integrate to do the formulas, I would love to do that. Let's see if there's one that's okay to do. Let's do 5/116. All right, and there's just a little piece of information I want to give you. I know you could arrive at this on your own, but the load curve looks like this. In other words, you build from 0 up to a value of 480 Newton per meter. Well, remember the equation here, because this is a slope, is y is equal to mx plus b. b is equal to 0. So the slope is 480, because you go from 0 to 480. Times x, and what's my y value? Is the load, right? The W. So in other words, everywhere here, it's just equal to the slope of that line. Okay, and so use the equations for this. Because I don't really see one that really works very well aside from that. Let me see if I'm just going to take 1 second here and see if I can find a better problem than that, because there's some flaws in that I don't really like. There's not some flaws, it's just there's a couple ways to solve it. Nope, can't find anything. Okay, so there's your homework, 570, 572, 5116. So please come to class Monday, prepared to ask questions, and then we'll get started with chapter 6. Guys, have a great weekend.